We'll talk about memory latency tolerance, but before that, I'd like to wrap up DRAM control. But before that, there are Lab 5 results. I think these should be available to you. I'd prefer this to be a single modal distribution over here. It's bimodal right now. So why don't you figure out what was wrong and fix it? And if you're here, I don't know what happened. So you should definitely talk with the TAs. Oh, they didn't turn in. OK. Well, I guess it's not too bad if you don't turn in if you've already gotten 10% extra credit. But I'd like you to still try to turn in to learn the material. And I'm actually happy that the median is 93.8, which means that people are actually doing the labs. But I would suggest trying to shift this distribution. Even if you're late, learning the material matters. Some reminder on assignments. So we're going to switch, or maybe some of you have already switched to C-level simulation. Lab 6 is C-level simulation of data cache and branch prediction. How many of you started? Oh, that's good. That's a good fraction of whoever is here. And you're enjoying it? Yeah? A little bit. Is it better than RTL level? You prefer RTL level. All right, I'll talk about that in a little bit. And homework 6 will be due April 10th. We've extended the deadline a little bit. And we will have a midterm too still. And just a reminder, well, in case you didn't know, I know that you guys all know you have very good attitude toward this course. The goal is really learning. So the course will continue to move quickly, so keep your pace. And if you need any help, talk with me and the TAs. Certainly, we cannot do or debug the assignments for you, unfortunately. Or fortunately, actually. You don't want that to happen anyway. But we can give you suggestions. And my goal is to enable you to learn the material. So even if you haven't submitted or if you didn't get a good grade on Lab 5, feel free to turn it in after the course is over. You can still learn the material that way, right? And you never know which principles you will use where, at what point. In a sense, that's the best attitude to learning, right? You just take it all in, and somehow it meshes with everything else that happens here, and eventually you don't even know if it'll affect you in the end, right? If there's a more difficult field than figuring out what's the best platform to design 20 years from now, that's really the field of psychology, right? You don't know what happens here. It's not clear if we will ever know. OK, that said, since we're switching to a different simulation mode, I'll talk about simulation a little bit. And I like calling it the field of dreams, actually. You're really exploring some field of dreams that you have. But there's always reality. So an architect is really, in big part, actually, a dreamer or a creator. You're really creating things in the end, right? And simulation is a key tool of the architect. Without simulation, you cannot actually survive. In fact, real architects do simulation also, right? They actually design buildings, put things together. And simulation enables the exploration of many dreams and a reality check on the dreams also. And deciding which dream is better. You have so many dreams to choose from, right? Which one is better? And you're doing that, actually. You're going to do more of that with the higher level simulation. It also enables the ability to fool yourself with the dreams, unfortunately. You can do this with any simulation, actually. RTL level simulation doesn't matter. I guess it's harder to do it with hardware, real design, in the end. But you can fool yourself with any simulator you build if you're not careful. So why are we doing high-level simulation in this course? So in the past, if you took this course maybe 5-6 years ago, you wouldn't do high-level simulation, at least maybe this much high-level simulation. But we added these labs because it's really important. And the problem with the low-level simulation or RTL simulation is it's really intractable for design space exploration. It's too time-consuming to design and evaluate, especially a large number of workloads, evaluate the design with that. Especially if you want to predict the performance of a good chunk of a workload in a particular design. How long would it take for you to simulate 1 billion instructions using the structural Verilog of a full processor? Even a simple processor, right? It'll take a while, right? Even your simple, 5-6 instructions takes a long time. And especially if you want to consider many design choices, think about all of these multiplying, right? You're simulating one workload for a really long time, let's say until completion. You're doing it over 1,000 workloads, and 1,000 may not be enough also. And you want to consider maybe a million different design choices. In fact, a million is not an unreasonable number when you're actually building a processor at Intel, AMD, NVIDIA. You might want to, because there are so many knobs that you actually build in the processor, right? And on top of that, there are algorithms too, right? Cache size associated with block size. Well, I have a bug over here. I got to fix the bugs. OK. Memory control and scheduling algorithms, all of them take time to evaluate, right? How do you evaluate them? In order versus out of order execution, even something simple like this. And even within out of order execution, you have so many design choices, right? And you actually need to design a processor at some point that has some, that satisfies some metrics based on the design choices you make. And you can imagine more, right? So the goal of high-level simulation is to explore these design choices quickly to see their impact on the workloads we're designing the platform for. And on top of this, you can even add other things, right? You also have the platform, right? You have the interconnect, you have perhaps other processors, you have memory. And there are different goals in simulation. And I'd like to spend some time on this because this is really important. And probably whenever you do engineering or design new things, you'll do simulation. One goal is to explore the design space very quickly and see what you want to potentially implement in the next generation platform, right? Do you want to do in-order execution or out-of-order execution? Propose as the next big idea to advance the state of the art. That's another thing that this enables, right? If you can explore the design space quickly, you can get to these big ideas much more quickly, right? And here, the goal is to mainly see the relative effects of design decisions, right? You don't really care whether one design decision buys 1% more performance or 10% more performance. You just want to see the relative effect, right? That's the key goal in this design space exploration. The second, perhaps an opposite goal, maybe the extreme end of the continuum, is maybe you want to match the behavior of an existing system exactly, and behavior meaning the exact implementation behavior, so that you can debug and verify it at cycle level accuracy, right? Basically, you want to see every cycle. You want to be exact at the cycle level. And maybe, on top of this, propose small tweaks to the design such that you can actually improve performance or energy or some other metric, right? Now, this is a totally different goal, right? Very different from exploring the design space very quickly. Because here you want to really match. Let's say you've designed Pentium Pro, and later you build a simulator that matches it exactly. And actually, that's not exactly how it happens, but that's what a lot of people who validate processors do. They use a simulator that hopefully matches the behavior exactly, and then they try to fix the bugs or maybe improve things a little bit. So here, the goal of the simulator design is very high accuracy, right? Here, you really want high accuracy. You don't necessarily, and you really want accuracy at the cycle level, at the nanosecond level. Yes?
So when you're doing high-level simulations, but actually when you synthesize it, like the synthesis changes for each node you're targeting, or the standard cell libraries that you use. So there's a lot of variation when you synthesize, right? Can you actually get a good feel of what performance you'll get just with C-level simulation?
Yeah, that's right. You could. Why not, right? Here, you don't even do synthesis at that level, at the high level, right? But your target is to look at the algorithmic effects. For example, in-order versus out-of-order execution. You can get what is the benefit if you actually implement this nicely at the low level, right? Out-of-order execution provides, let's say, I don't know, maybe you'll get 50% performance benefit at the high level with some inaccuracy. And when you implement it, maybe you'll get 30%, right? Yes? If you're not doing this one, you mean? Or if you're doing this one?
So are you saying in the second one you're doing RTL simulation?
Well, it could be, yes. It could be an RTL level. It could still be C level, actually. There are shades of gray over here also. But you can, to answer your question, you can look at energy at all of these different levels. The question is how accurate you will get, right? So one thing you could do, for example, if you're doing C level simulation, let's say not RTL level simulation, you could associate actions. Let's say you count the number of load accesses to the cache, and based on some other energy model, you actually have a nanojoule number for that, and you multiply those two, and you get the energy spent across the entire execution of the workload. Does that make sense? So you can actually get all of these numbers, yes?
Is that how systems are designed in industry as well?
That's right, yeah. And we'll get to that, actually. But usually you don't magically come up with a dream and implement RTL with it, right? You first need to figure out, like, let's say you're starting from scratch. What do you want to implement in a processor? And then you have so many choices, right? In-order and out-of-order execution is a very good example, for example. Do I want an in-order processor or do I want an out-of-order processor? Industry doesn't design both of them at RTL and pick at the end, right? You actually need to do this high-level simulation to figure out which one actually satisfies the metrics that you want to optimize for across the workloads that you care about, right, as industry. So you need to do this unless you want to design all of these options in RTL, right? Okay. And you can actually, in terms of metrics, you can model energy, you can model performance, you can model reliability at all of these different levels. What changes is the level of fidelity, potentially. Okay. So there are other goals in between also, right? Let's assume that you've explored the design space over here a little bit, and you say, oh, out-of-order execution actually provides huge performance benefit on these workloads. So let me go into a little bit more detail, and let me make it a more detailed simulator. Maybe before you didn't model some of the things correctly, right? Maybe you didn't model all of the store load dependencies accurately. That's why you got a 50% performance benefit. But you go one level below, you actually model the load store queue more accurately. Again, what's more accurately? Hopefully in a way that's closer to the implementation, right? That way you get a better idea of the performance. So you go to the next level. And then the other goal is to gain confidence in your design decisions made by higher level design space exploration, right? You do the higher level design space exploration. So you want to build perhaps smaller models to gain confidence in those. So that's why you need to go down to the lower levels. And actually, depending on your goal, you may stop at a particular level. If you're designing a processor in the end, of course, you need to go all the way, right? You need to do the hardware design. But your goal, if your goal is research, for example, maybe you start exploring the design space and you go some levels, but you may not even go into the RTL level, right? Because your goal is to figure out the big ideas at that high level, and maybe someone else will take those ideas and do the implementation, right? That's what a lot of computer architecture researchers in the field do, for example. Systems researchers also. They may not necessarily design a processor because that's a lot of effort, right? There's limited amount of time in the world, and your goal is to come up with bigger ideas versus actually implement those ideas. These are actually goals that are contradicting each other in the end. Right? OK, so there are actually three metrics. The way I like to think about simulation is there are three metrics to evaluate a simulator. And these lead to trade-offs. Speed, the speed of the simulator, flexibility of the simulator, and accuracy of the simulator. So speed is basically how fast the simulator runs, basically how many instructions per second, let's say, it can simulate, or how many cycles per second it can simulate in the system. Right? Flexibility, how quickly can you modify the simulator to evaluate different algorithms and design choices? Right? That's also important. Because if you cannot modify the simulator to switch between in-order and out-of-order execution easily, then you have a problem, right? And RTL is very difficult to do that, for example. That's why we don't have another lab saying, now that you've built your pipeline processor, build an out-of-order one. Right? It's easier to do that at the C level, though. OK, accuracy, how accurate the performance or energy or some other reliability is another thing, by the way. Numbers the simulator generates are versus a real design. This is basically your simulation error. And you can trade off all of these metrics. And the relative importance of these metrics, again, varies depending on where you are in the design process and what your goal is. Right? So like everything else in the world, the answer is it depends. Which one's important? Well, it depends. So let's take a look at how we can trade off these things. Basically, speed and flexibility, simulator speed and simulator flexibility affect how quickly you can make the design trade-offs, right? And you can make and evaluate the design trade-offs. Because in the end, you're bound by that time. And accuracy of the simulator affects how good your design trade-offs may end up being, right? If you're completely inaccurate at the high-level simulation, maybe the things you decide could be bogus, right? If you don't implement, for example, out-of-order execution, at least to some level of fidelity, you may think that it gains a lot more benefit than you could afford the implementation cost for. Right? That's why it's really important. That's why this is actually partly art again. And how fast you can build your simulator is also affected by accuracy. This is the simulator design time. That's another constraint, right? How long are you going to spend to design your simulator? And these things are actually really important. For example, when Intel was designing Pentium 4, the simulator was one of the bottlenecks. And they wanted a simulator where they can explore the different design trade-offs really well, but they didn't have it in time. So they needed to actually get some really good programmers who know simulation to actually do the simulation. So if you actually know how to do this well, you can also make a lot of money, by the way. Not that that's the only goal in life, but OK. So flexibility also affects how much human effort you need to spend modifying the simulator, right? It's not only how quickly you can get to the design trade-offs, but also how much effort are you spending. And what happens usually is, as the simulator grows, even if it's a high-level simulator, as you start adding more and more knobs and things, if you don't do it in a modular fashion, what happens is it becomes very inflexible. It becomes very, very difficult to modify. So it's good to start with a good baseline, but over time, if your simulator evolves in a way that actually leads to less flexibility, it's good to sometimes start from scratch. In fact, that's what some companies do. They start from scratch to do the simulation. OK. And you can trade off between the three metrics to achieve design exploration and decision goals. OK. So in high-level simulation, so one example, for example, if you can reduce the accuracy level a little bit to improve speed and flexibility. That's a key trade-off. And this is you usually can get at most 2 out of these 3. It's very difficult to get all of them perfect. So normally at different levels of simulation, you pick at most 2 out of 3. At the high level, for example, you pick speed and flexibility over accuracy a little bit. At the low level, you pick accuracy over speed and flexibility. Right? If you come up with a simulator that's good at everything, let me know. That's going to be very difficult. So high-level simulation. The key idea here is to raise the abstraction level of modeling to give up some accuracy to enable speed and flexibility, and to also enable quick simulator design. Right? So there's a big advantage to this, but of course there's always a disadvantage as well. You can still make the right trade-offs and can do it quickly. Why? Because all you need is the modeling of the key high-level factors. You can omit potentially corner case conditions. Right? Now, what is corner case and what is not? That's the art of simulation now. You've got to somehow decide that. If unaligned accesses are not going to happen that much, then maybe you don't model them at the very high level, right? Or maybe you do it this way. You can imagine many techniques. This is where creativity comes in a lot. Maybe you assign some probability to unaligned accesses and assume that randomly some accesses take, with some probability, some accesses take longer than others, right? Instead of modeling everything really, really accurately, right? If you do it at the gate level, then you actually have to model every single instruction accurately. Whereas at the high level, you can say, oh, with some probability, this instruction will take 5 cycles. With some other probability, it'll take 10 cycles. With some other probability, it'll take 20 cycles, right? You can have a really abstract model. And you may choose not to model some things. For example, you may choose not to model at some level of simulation. Load store queue is a very complex part of the design, right? You may choose not to model the case where a load actually matches 4 different stores in the store queue, right? Because that check actually takes a lot of time. OK? And again, all you need is to get the relative trends accurately, not exact performance numbers. And hopefully, if you can achieve this, then the high-level simulation's goal is done, right? The disadvantage is, of course, whenever you give up accuracy, you always open up yourself to the possibility of wrong decisions, right? That's why you got to be careful when you do this. How do you ensure you get the relative trends accurately, right? You assumed unaligned accesses are not common. What if it turns out in the workload you care about, they do unaligned accesses all the time? Right? That's why you have this progressive refinement in the end. You don't stop with the high-level simulation. You start with the high-level models, explore the design space, and then come up with some medium-level models that are less abstract, progressively refine different parts of the system. And then go down and design low-level models, RTL with everything modeled. And then you do the real design. By the way, these are not the same thing also, right? RTL also has simulation error, right? In the end, you're doing simulation error until you get the hardware. Because hardware could be different from RTL. Maybe not too much, but slightly. In fact, in some processor designs, RTL differs from hardware by 3 to 4%. That's the simulation error at the RTL level, right? You don't get the exact cycle counts. Why? Because people optimize design at the lower level also, right? And then the question is, how do you actually try to go and match these two things after you build the hardware? That's the part of the verification and validation. Okay. So as you refine, as you go down the above list from top to down, abstraction level reduces. Accuracy hopefully increases, but not necessarily if you're not careful, right? Your accuracy may actually degrade or not increase. Because again, you're doing simulation. All of these are simulation. And speed and flexibility reduce because you're adding more and more detail. And you can actually loop back and fix the higher level models. And that's actually a very powerful thing if you go down to the lower level. You can go back and say, oh, maybe the higher level model had an error here in its out-of-order execution modeling. So I'll fix it with what I've learned from the lower level model. And that's actually the benefit of a company that has designed many, many products, right? You actually have all of this information. You can even do machine learning and figure out what decisions were good and bad and design a better simulator the next time you're starting out. OK, so in this course, basically a good architect is really comfortable at all levels of the refinement, including the extremes, actually. So if you want to make quick design decisions, you would like to be comfortable at the high level. And if you want to implement something, you would like to be really comfortable at the low level. So this course, as a result, is designed to give you a flavor of both. So you've done, well, you haven't done this yet, but you will do high-level abstract simulation in labs 6, 7, 8. And by the way, this is not the most abstract simulation model. It's still reasonably cycle level, cycle accurate. Not perfectly, though, because, for example, the DRAM controller that you will design in lab 7 will not, well, with lab 6, you're assuming some memory latency because it's certainly abstract. But in lab 7, the DRAM controller you design will not look into a lot of parameters. Refresh will be omitted, for example. Right? You won't have to deal with write-read latencies, for example. And you've also seen low-level RTL simulation. And hopefully you enjoyed it. If you're not fully done, please complete the labs. OK, so there's optional reading. There's a lot of reading on simulation. But this is one paper one of my students did recently. It's a very short paper on Ramulator, basically a fast and extensible DRAM simulator. If you're interested in this, you can take a look, since we've covered DRAM also. OK, any questions? I could actually have a long class on simulation with more detail, but this is more than what we had before. No? Yeah?
Do people in general who make the high-level C models also try to do the synthesis and check out how it...
No, that's very difficult. So that's a different goal. So OK, let me tell you a little bit about how this works. Actually, industry does exactly this, basically. It's really a progressive refinement. And they start with high-level models. In fact, high-level models could be spreadsheet models, what I call the spreadsheet simulators. You actually have some numbers gathered from traces of workloads. And you have the number of loads, number of stores, I don't know. Imagine things like that. And then based on past designs, you have an idea of how long each of these will take. And you feed them. You have a complex equation as a simulator that takes all of these inputs and gives you an estimated cycle count, let's say, if it's a performance model. Right? It's based on pure trace analysis plus a spreadsheet that takes the analysis of the trace and an equation that outputs you, that gives you the number of cycles it'll take to execute, or number of cycles, the performance of a particular design. Right? You could imagine that. It's kind of an analytical model. Right? You're really abstracting even higher. You're not even doing simulation in that case. Well, you could consider the trace analysis simulation. And then you progressively refine this. So your question was basically, do you actually try to synthesize this high-level model, right? You could if you have enough detail, but that's not necessarily simulation in that case, right?
So the question is, if you're not in a company, how do you verify that
Oh, I see. That's a tough question, right? Then basically you're asking how do you actually verify your idea? In the end, the validation of an idea is eventually the implementation of that idea in a system, right? The real validation. But then if you're not in a company, you have other goals also. Your goal is not necessarily ensure that the idea actually works in a real system, but maybe it'll generate other ideas, right? If you're doing research, right? If this idea spawns some other ideas that are better, that are eventually implemented, then maybe your idea is successful in that respect, right? Again, it depends on your goal, right? But you cannot verify. In the end, the right answer is you cannot verify without really building it. Okay? But maybe somebody else will build it, and they'll verify it. Yes?
And by really building it, you mean like going to manufacture, or do you build it on an FPGA first? And then
Oh.
how do you
Again, it depends on your goal, right? An FPGA is not a real design necessarily, right? So an FPGA is definitely like building it in an FPGA is probably somewhere around here. Right? It's still a prototype, if you will. I would consider that a simulator also, in a sense. It's really a prototype / simulator. Okay? But one anecdote again. Even if you build something in an FPGA, that doesn't mean that the company who wants to take that idea believes you. Right? Because it's just an FPGA, right? You're actually designing it at 200 megahertz, let's say, maximum. Whereas the company is going to try to design it at 6 gigahertz. Right? You run into other issues. But it's still again, you're hopefully closer to that real design. Okay. So hopefully this gives you a good idea of simulation. Any other questions? All right, let's move on to memory latency tolerance techniques. But before that, we'll finish DRAM. And we're going to dream a little bit more, actually, in DRAM. But before that, there's another seminar on April 3rd. It's before our class. So again, you can go to the seminar and we can walk back and get food in between, I guess. This is Professor Moindin Qureshi from Georgia Tech will be giving a talk. And you may remember this name if you read this MLP-aware cache replacement paper, right? Do you guys remember the MLP-aware cache? OK, good, that's good. So he's going to talk about architecting 3D memory systems. Again, very relevant to what we've discussed. Basically, he's going to talk about how to potentially use and enable 3D DRAM technology. This is basically, you have a controller at the bottom, and you have DRAM stacked on top of the controller, and maybe you have more DRAM stacked on top of it. That way you get controller and DRAM cooperating together, and you basically have multiple dies on the same chip, right? And then he'll talk about some of the design decisions related to it. So hopefully it should be interesting. A lot of the things that we've covered in this course. For example, how to design decisions that are made typically for conventional caches, as you can see over here, may be detrimental to the performance of DRAM caches because they exacerbate hit latency. So you can take I think you would learn from this seminar if you're able to attend it. OK, so you know these required readings. There are two. We talked about Bloom filters. Bloom's paper could be a little bit hard to decipher. So I suggest you take a look at sections. These are really short sections, by the way. These are less than a page. Sections 3.1 of this paper and sections 3.3 of this paper to learn more about the Bloom filter designs at the high level. Okay. Any questions? That was quick. Who likes attending these seminars, by the way? Well, that's good. Most of you, actually. Who doesn't like, who hates attending the seminars? That's the other, you don't like it? Which ones? Was there a particular one you hated?
I didn't really enjoy the one with Larry Page. Wait, no, the one about I can't even remember it. I didn't enjoy it that much.
You said Larry Page?
Well, I forgot his name already.
OK. This is someone from Google?
Yes.
Oh, OK. This is the one we went to.
Yes.
Oh, OK. Yeah, I see. OK, sure. Yeah, why not? You always have these differing opinions. That's a really good thing, actually. Someone can like the seminar a lot, and someone can hate the seminar, which is which is perfectly fine, actually. OK, let's talk about difficulty of DRAM control before we move on to memory latency tolerance. I think this is important because this points out some dreaming in design as an architect. So DRAM controllers are actually a pain to design because there are so many things that you need to consider, and these are increasing. First of all, you need to obey DRAM timing constraints for correctness, right? And there are many timing constraints in DRAM. Your required reading will be a DDR2 DRAM data sheet next week. You wouldn't like that, probably. And you can figure out all of the DRAM timing constraints. I don't claim to understand all of these timing constraints after looking at data sheets. But some things that we've discussed, there's WTR, for example, write to read latency. This is the minimum number of cycles to wait before issuing a read command after a write command is issued. And you have this because you need to turn around the bus, right? The bus can drive this way. And if you need to turn around the bus to do the writes or reads the other way, you need to wait for a while such that things can stabilize. TRC, this is the minimum number of cycles between the issuing of 2 consecutive activate commands to the same bank. This is a row cycling latency, basically. And this is kind of the key latency in DRAM. When people measure DRAM latency, they talk about TRC most of the time. And imagine more than 50 others. And when you're designing a control, you need to obey all of them. You need to, first of all, figure out whether you can issue a command given all of these constraints. And second, whether you obey it and which command to pick, right? You need to keep track of many resources to prevent conflicts. And we've discussed this before. There are many of them. You need to handle DRAM refresh on top of this. This is a critical thing that you need to handle. You need to manage power consumption. We very briefly discussed in one slide, if you remember. And on top of this, you need to optimize for performance and quality of service in the presence of all of these constraints. And reordering is not simple, actually. We've talked about reordering as if it's really easy, but in the end, we're really reordering things. We talk about instruction reordering, for example, in the processor, right? That is not simple also, if you think about it. It's not, in order is so simple. But once you start reordering things, you need to have a priority encoder, and you need to ensure that you obey the cycle time constraints. And fairness and quality of service also complicate the scheduling problem. It's not only for performance that you're optimizing. It's really all of these other things. And if you want to learn about the other DRAM timing constraints, definitely look at a data sheet. But data sheets are not tractable in general. So you can take a look at some of these papers that I mentioned over here. So this is actually only 1, 2, 3, 4, 5, 6, 7, 14 of the DRAM timing constraints. 14 important ones at least. So there are really interesting timing constraints like this, for example, 4 activate windows. This is the number of activates you can issue within a given number of DRAM cycles, like 4 activates. Why? Because if you actually issue too many activates, then you're actually overloading the system in terms of power. So you run into reliability issues. So DRAM controls actually, or DRAM specifications, limit the number of activates you can issue within n number of cycles. And you can issue 4 activates within 24 cycles over here, basically. It's kind of interesting, right? And you're hopefully reading the background sections of these 2 papers for operation. And this is becoming much more difficult going forward. Why? Because we have all these heterogeneous agents that are sharing the DRAM controllers, different agents. And you can imagine multiple of these, maybe multiple GPUs, right? And there's interference between all of these agents. And maybe you have multiple different memory types, right? You have some embedded DRAM over here, some 3D stacked DRAM, and some commodity DRAM. And you need to ensure the timing constraints for all of those. And they all have different timing constraints, actually. So you cannot design a single controller that works for all of them. So you need to really design different controllers. And we will see that there are other memories that are coming up, emerging technologies that require other controllers with slightly different characteristics. And there are many goals at the same time. You want to optimize for performance, fairness, quality of service, energy efficiency, ... So the reality is that it's difficult to optimize all of these constraints while maximizing performance, quality of service, energy efficiency. So the dreamer would always like to dream, right? Wouldn't it be nice if the DRAM control automatically found a good scheduling policy? Let's constrain ourselves with just a scheduling policy, right? Wouldn't it be nice if the DRAM controller did something like this? Can anybody guess how you can do this? No? Somebody said machine learning? Or did I imagine that? You said it? Yeah, machine learning. Yes, that's right. if you've taken a machine learning course, perhaps you could at least try to do this. And I want to talk about this so that it gives you an idea of a dreaming architect, right? And how you can actually evaluate this. And if you tell me that you got to design RTL to evaluate this, that's a bad idea. You could actually, but it'll take a long time to at least look at the high-level potential benefits of the idea. So the idea is to actually use machine learning. Because DRM controllers are difficult to design, it's difficult for human designers to design a policy that can adapt itself very well to different workloads and different system conditions. Again, the system is also dynamic, right? You have all these workloads coming in and going out. They have different requirements. And you're designing a DRM controller that needs to work well under many conditions, right? And we've seen a lot of policies in the past. They're all, even though we tried to improve the adaptivity of the policies, they're still based on human designers' intuition and decisions, right? So wouldn't it be nice if we could design a memory controller that adapts its scheduling policy decisions to workload behavior and system conditions using machine learning? That way the human designer perhaps just specifies, oh, these are some of the important system parameters you take into account. Come up with a good scheduling policy online, right? Sounds like a dream. It is a dream, actually. There's no DRM controller that does this today. But I think increasingly, as systems become more complex and more difficult to design, approaches like this would be very useful. I'll give you one example. Actually, in the past, the operating system, the disk latency, for example, is a big problem, right? It takes a long time to fetch data into memory from the disk. In the past, operating system used to do prefetching, right? And this prefetching was based on like simple access pattern prediction. What page you're going to access next sequentially. We're going to actually talk about this prefetching at the processor level in the next lecture. But actually, if you know a lot more about the system, you can design a machine learning-based policy that can do prefetching a lot more intelligently. For example, over time, you're running the operating system. The operating system collects a lot of information and says, oh, I figured out that at 3 a.m., Onur checks his email, right? So I would prefetch the email program and potentially the emails, and potentially some links along with it, to memory when Onur is about to check his email, right? And it's a machine learning algorithm. So this was a dream, but it's already in, well, I don't know about Apple, but it's already in a lot of the Windows products. Windows actually has such a prefetcher that operates using simple machine learning principles, maybe not very sophisticated. Right? And I bet some of these other operating systems also do things like that. So it was a dream at some point, but it's reality now. So maybe this could become a reality. As systems become complex, and as you need to take into account a lot more things to make design decisions, you may need to resort to techniques like this. So it's good to know. Multiple areas, actually. So the observation here is reinforcement learning actually maps nicely to memory controller. How many of you know reinforcement learning? Yeah? How many of you know about Pavlov's dogs? More people, yeah? That's basically reinforcement learning. So what Pavlov did, Ivan Pavlov was a psychologist. What he did was he trained the dogs such that they could associate the ring of a bell with food coming. Right? That was at least one of the things. So how did he do this? Basically, he rang the bell and gave the dogs food. And after doing this maybe 3 or 4 times, the dogs were quick enough to realize that, oh, after the bell, the food will come. So what's happening here is you're reinforcing the relationship between a bell and food, or a state, or kind of action, and a reward. The action is really the bell ringing, and the reward is food. As you keep getting food, every time the action happens, your learning is reinforced. Okay? And later, after a bell, if you actually don't get food, you will start forgetting because your reinforcement reduces, right? So that's the reinforcement learning. And the same principle has been applied, actually, to systems. So for example, people have designed ways of automatically flying helicopters using reinforcement learning. Well, initially, the helicopter hits some places and eventually learns how to fly by itself, right? It may not be the best algorithm to use initially, But over time, you can learn actually how to fly automatically. So memory control is actually kind of lucky to have a similar behavior, right? Basically, memory control, you can think of it as a reinforcement learning agent that can dynamically and continuously learn and adapt, learn and employ the best scheduling policy. So this is at a high level what reinforcement learning looks like. Basically, you have an agent, a dog, interacting with the environment, doing an action or some action is happening, and then you're getting a reward and also a state. So given a state, and actually this way you can educate the dogs to do something, right? In fact, there are really cool stories in psychology, but we won't get into that. For example, B.F. Skinner educated a lot of pigeons to deliver messages in the Second World War. So he has these pigeons. Maybe we can talk about that later. Basically, given some state, if the pigeons do some action, deliver the message, they get a big reward. If they don't deliver the message, I don't know, they get caged or something, right? Although Skinner was a big believer in positive reinforcement, not a negative reinforcement. So he believed that negative reinforcement is a bad idea. No punishments. You always do positive reinforcement. That way you learn better. That's what his thing was. So you don't get you get a reward or don't get a reward. So given a state, if you take some action, you get some reward. And over time, you can associate the state and action pairs with the rewards that you're going to get. You can actually do this in the long term or short term. And if you look at the scheduler, it kind of looks like this agent, right? Given a system state, if it takes an action, it gets some data bus utilization or some reward over time. And you can actually figure out what that utilization was, and you can attribute to state and action pairs. And the overall, over time, you need to read some papers to figure out how to do this. You can learn to choose actions to maximize some long-term reward value. You can actually weight the rewards such that you can maximize the long-term performance. And that's the idea of a DRAM controller that operates based on these principles. You can dynamically adapt the memory scheduling policy via interaction with the system at runtime. You can associate system states and actions, or commands, think of them as commands, with long-term reward values. Each action at a given state leads to a learned reward, because you can actually measure what your reward is. And you can schedule the command with the highest estimated long-term reward value in each state, because you know your state, right? And you can continuously update reward values for different state action pairs based on feedback from the system. And you're making all of these decisions very, very quickly, right? You're actually making billions and billions of decisions within the course of seconds in the processor, right? Especially if you have many memory controllers. Okay. Does that make sense? So you may have lots of questions, and I'm not going to talk about that. That's just to give you the high-level idea so that maybe you can apply this somewhere else. What are the states? Well, there are many, many potential things that could be part of the state, right? What are the actions, and what are the rewards? So reward function is actually a difficulty. This really depends on what you're really trying to optimize for, right? So you could potentially say, I get a +1 reward for scheduling read and write commands, 0 at all other times, because all I care about is really reading and writing. This is good if the goal is to maximize data bus utilization, because this doesn't really take into account whether you're fair, right? This just cares about maximizing the issuing of read and write commands. And over time, maybe you'll learn policies that are actually good for maximizing this reward. What are the state attributes? Well, it could be many, many things. But if you look at that paper, it could be number of reads, writes, load misses, number of pending writes, reorder buffer heads waiting for the referenced row, request relative order in the reorder buffer. If you're having out-of-order processors, we could actually imagine many, many things. And the selection of these states that need to be fed into the reinforcement learning algorithm is actually a problem itself, right? How do you actually figure these out? You're actually putting the complexity somewhere else, but hopefully this is a simpler problem than coming up with a policy that's good online. And actions, well, actions actually could be many, many things. These are basically the DRAM commands in the end. And you could potentially issue a no-op in DRAM also, right? If that maximizes long-term reward. I'll give you one example. Well, you could actually, for example, sometimes you may want to leave the data bus unutilized for a while by issuing a no-op. Why? Let's say you have a row that's open, and you have a request that's to another row in the same bank, maybe you don't want to close that row right away because one cycle later some other request will come to the same row. If you actually wait for one cycle, do not issue a pre-charge, do not get rid of that row, you could actually exploit that row buffer locality and service that request quickly and improve system performance, right? But existing DRAM controllers don't do this. Their goal is to maximize the, basically, they don't have this foresight, if you will. They're kind of myopic. They don't look into the future. Whereas a learning algorithm like this may potentially be able to figure out that case, and it can say, oh, in the past, when I was in this state, if I issued a no-op, it was actually better. And how can it actually figure out issuing a no-op? Well, that's actually one of the interesting things in machine learning. Sometimes you want to explore the space. And how do you explore the space? Sometimes you actually issue some legal commands that are random. With some low probability, you say, oh, my state action pair tells me that I would actually maximize my reward if I issue this command, but I'm going to pick some other random command just to explore the space a little bit. Right? That way you can actually figure out new policies also that you may not have figured out easily. Right? That's kind of the nice thing about machine learning. You can actually explore the space much better. It's very different from a very fixed policy like what we've discussed, right? Thread cluster memory scheduling, for example, or row hit first policy. OK, so what is the performance benefit? So as a dreamer, you got to simulate. And this is the simulation using a system level simulator, C level, similar to what you're going to build, but more detailed. And this shows basically what your performance is. This is basically some multi-threaded applications, scientific applications. I believe it's a 4-core model with a single memory controller. This is the performance of row hit first scheduling policy, FRF-CFS. This is the performance of an in-order scheduling policy, FCFS. So there's a huge performance difference. Right? And if you do reinforcement learning, that's the performance improvement. It's about 20%, let's say, at least with this model. And this is the optimistic policy where you don't have any constraints. This is kind of the upper bound, ideal, if you will. If you can design an ideal memory controller that actually doesn't, the only constraints over here are actually the data bus constraints. So it's even more optimistic than an ideal controller, right? Because you're assuming everything is actually a row buffer hit. Okay? So it seems like there is some benefit to this. It's about 20%. And the benefits may be higher over here when you have different kind of buses. OK, so what are the advantages and disadvantages of the idea? There's always advantages and disadvantages. Basically, if you do something like this, you can adapt the scheduling policy dynamically to changing workload behavior to maximize a long-term target. Right? If you think about first ready, first come, first serve, row hit first, it's very short-term. You want to maximize row buffer hit rates. But that's not necessarily performance, as I just discussed. Right? It reduces, hopefully, the designer's burden in finding a good scheduling policy. And designer, and this is one of the advantages of machine learning if you can successfully apply it. Designer can specify only what system variables might be useful to consider in the algorithm. That's the system state. What target to optimize. That's the reward function. But not how to optimize it. And hopefully the underlying algorithm optimizes it. Okay. There are disadvantages to it also, right? Actually, one big disadvantage as a designer is it's a black box to the designer, right? The designer is much likely to implement what she cannot, much less likely to implement what she cannot easily reason about. How do you reason about such a policy? And this is always the downside of any machine learning policy. It's very difficult to reason about and debug what's going on. Debugging is a little bit easier than reasoning about. How do you specify different reward functions that can achieve different objectives? This is actually, again, true for any application of machine learning. If you have one objective, you may be able to easily specify a reward function for it. Data bus utilization is one example. What about fairness? What about quality of service? How do you do that? It's not that easy. And what about the complexity of it? Then how can you build this in an easy-to-implement manner? Right? Because the complexity of the algorithm may be very high. Any questions? Does this sound interesting? Yeah?
You have a dedicated hardware running these machine learning algorithms?
Well, it's a memory controller, yes. You could, if you're doing it at the memory controller, you have a dedicated hardware. That's right. But if you're doing, let's say, prefetching, a machine learning-driven prefetcher at your operating system, then it's in software. And you can still use the same algorithms, but your implementations will vary. There's also one more other thing, what algorithm to choose in machine learning. So if you've taken a machine learning class, you've probably seen many, many algorithms, right? Many approaches to machine learning. And not all of them are equally applicable here, right? For example, in this case, OK, let's take the example of branch prediction, right? Actually, that's another place where you can apply machine learning. And we did see it, right? Perceptron. A very simple perceptron is actually a very simple neural network, which is really a machine learning agent, if you will. And you can apply it to branch prediction. Over there, you immediately know whether your decision is correct or not, right? Because if you're optimizing for branch prediction accuracy, after the branch resolves, you know whether you did the right thing or not. So you can immediately feed that back to the algorithm. It may be a little bit difficult to do that if you're optimizing for long-term performance in memory scheduling. Because in branch prediction, the problem is a little bit easier in the sense that you get this quick feedback on correctness of your decision. Whereas here, what is a correct decision? Just the fact that you utilize your data bus immediately may not be the best thing, right? Because it may turn out that because you utilize your data bus very well, you're actually denying service to somebody else in the system, right? OK? So you may need a different algorithm for this. OK, I won't go into any machine learning anymore. But this is something I would definitely suggest. I've already suggested to you a lot of courses, right? OS courses, compilers, parallel programming. 418 is a good course, for example. But machine learning is a good course, too, going forward as system designers. And you're lucky to be at CMU, actually, because we have a machine learning department here. And we may be the only university with a machine learning department. Yes?
Is it important to be doing dynamic memory, to be dynamically altering your scheduling policies? Or can you do simulation work with a basic test set?
That's an excellent question. You're asking a really excellent question. And when we explored this idea, we did actually look at that question. It's a lot better to do dynamic updates to the policy. But basically what you're suggesting is, why don't you actually figure out, still using machine learning offline, a really good algorithm, and just implement it. Again, you don't know how it works. Maybe it's a black box. Just implement it, but never change the policy. You could actually do that in simulation, and we did that. It turns out dynamically altering the policy is much better. Okay. Because now you're adapting to system conditions that dynamically change also. But doing what you suggest is better than FRF-CFS, for example, or hit-first scheduling. OK. Maybe this is a good place to take a break. It's an early break for you guys, but maybe you can recharge for 4 minutes, and then we can come back with a different topic. We have a lot to cover, and we'll start memory latency tolerance. And these are some readings for you. These two are required. These are optional. So remember latency tolerance. We've talked about this, right? When we talk about out-of-order execution. Out-of-order execution's main benefit is tolerating latencies. If everything was one cycle, out-of-order execution wouldn't give you any benefit, right? And an out-of-order execution processor tolerates latency of multi-cycle operations by executing independent instructions concurrently. This is a very good way of actually tolerating latency. While you're waiting for something, do something else, right? That something else could be independent instructions in out-of-order execution. That something else could be something else from some other thread in fine-grained multi-threading or hyper-threading, right? And out-of-order execution does so by buffering instructions in reservation station and the reorder buffer, if you remember. And remember, we talked about instruction window. This is the hardware resources needed to buffer all decoded but not yet retired or committed instructions. Does that make sense? Reorder buffer is basically stores all of those instructions, but you need resources across the processor, like physical register file entries, reservation stations, load store queue entries for those instructions that are not yet retired but decoded. And I think I've asked you this question. What if an instruction takes 500 cycles to execute, right? how large of an instruction window do you need to continue decoding? If your issue width is 4, and if the instruction takes 500 cycles, you need an instruction window of 2,000 entries to keep decoding, right, without stalling. Does that make sense? OK. We've already discussed this at some point, so you can go back to that lecture. And we've also talked about how many cycles of latency can out-of-order execution tolerate, right? The problem with any kind of execution is when a long latency instruction is not complete, it blocks instruction retirement. If you have an in-order processor, this is actually much more severe, right? Even in a dependency, you block progress in the pipeline. And this is true because we need to maintain precise exceptions. That's another way of looking at it, right? If you don't need to maintain precise exceptions, you could retire everything out of order, and you wouldn't need to block retirements, right? But there's a good reason why we have precise exceptions, as we've discussed. And incoming instructions actually fill the instruction window. This is the reorder buffer, reservation stations, load store queues, register file entries. And once the window is full, the processor cannot place new instructions into the window. And this is called a full window stall. Basically, you have a full window stall. You cannot bring in any more instructions into the machine. And this kind of full window stall happens really early in an in-order processor, if you want to think in order. But don't think in order. Let's think about high performance right now. A full window stall prevents the processor from making progress in the execution of the program. So let me give you an example over here. So let's assume you have an 8-entry instruction window, and you have this load that takes a cache miss, takes hundreds of cycles, and then branch that's dependent on it. And then you predict that branch, and you fetch all these independent instructions that can be executed without waiting for the load and the branch. But they cannot be retired. You need to preserve the results in the machine structures. As a result, your window becomes full, and younger instructions cannot be executed because there is no space in the instruction window, right? And this could be a load that also misses the cache, in the cache. But you cannot even bring it into the machine, right? So if you had one more entry in the instruction window, you could have actually brought this load into the cache, not into the cache, into the machine. You could have executed it. You could have started the miss that it generates. And you could have serviced that miss in parallel with the miss that's generated by this load. But just because your instruction window was only 8 entries, you couldn't do that. So you lose a lot of performance, right, because of that. And the processor needs to stall until this L2 miss is serviced. And once this is serviced, once this load is done, you create a space. You create space in the instruction window such that you can actually bring in this next load, only to stall again soon, because it'll take a miss that takes hundreds of cycles. And long latency cache misses are responsible for most full window stalls. I'll give you some data. This is actually based on a model, based on the paper that is required reading. But it's based on a model of Pentium 4-like processor, circa 2002. And this is data averaged across many memory-intensive workloads. This is a subset of the workloads that Intel used to design their processors at the time, and with some simulator. Again, this is simulation. That's the field of dreams. But it gives you a lot of insight. You can analyze the data, right? So this is averaged across all of those workloads. What fraction of the execution time is spent stalling? Basically, what fraction of the execution time? You examine every cycle. Is this cycle, and you ask the question, is in this cycle the processor experiencing a full window stall or not? Well, most of the cycles, the processor is experiencing a full window stall. Sounds bad, right? You're designing the processors, and they're waiting for data all the time. Well, that's still true. And it turns out if you analyze this in the simulator, you figure out that most of the full window stalls are due to L2 cache misses in this particular model. So why is this happening? Well, it's happening because applications need data, and memory latency is long, right? And it's not easy to reduce it. In a later lecture, actually, we will talk about methods for reducing DRAM latency. But these actually come at a cost. Hopefully not too much cost, but we'll see this in a later paper, because it's really important. And even if we reduce memory latency, it's still long. That's the unfortunate fact. So just to give you some numbers, I like quoting the Xbox number. Xbox 360 had a memory latency that's longer than 600 cycles, for example, at the time. Its frequency was not that high, actually. It's just because it's so far and memory is large, and it takes long to access memory. Because there's a fundamental capacity latency trade-off, right? As you increase the capacity of memory, your latency increases. And contention for memory also increases latencies, right? If you have many things contending for memory, remember the load latency curve that I gave you in the last lecture? As you increase the load in the system, the latencies start shooting up. Right? That's very fundamental. That's true for memory also. Okay, so how do we tolerate stalls due to memory? In the next 2 lectures, we're going to cover things like that, maybe 3 lectures. There are 2 major approaches. One is reducing or eliminating these stalls, right? And you could do that by reducing the memory latency. Let's assume that you have a given memory latency. Or you can tolerate the effect of a stall when it happens. Thus, out-of-order execution, in a sense, does that, right? It tolerates the effect of a stall by executing independent things. There are 4 fundamental techniques to achieve these, and actually we've seen all 4, except we haven't gone into detail in one of them at least. You can cache, prefetch, do multi-threading, or do something else, or do out-of-order execution, right? And data flow, you can think about over here, but it could be a different model. And many techniques actually have been developed to make these 4 fundamental techniques more effective in tolerating memory latency. Let me cover these briefly. Caching, we've already covered, right? And modern processors use all of these techniques, by the way. If you look at a processor, a high-performance processor at least, it uses all of these techniques. Caching, I don't know of a processor that doesn't use caching today. But that's a trade-off also, right? If all you're doing is random access, caching is a bad idea. OK? So this is widely used, simple, effective, but inefficient and passive, right? If, for example, cold misses, we've discussed. If you get a cold miss, caching cannot eliminate that. And not all applications or phases exhibit temporal or spatial locality. So maybe it's good to look at some other techniques. Prefetching we will look at, especially in the next lecture, but we will look at a special form of prefetching in this lecture. Basically, all of these ideas, by the way, were introduced in the 1960s. And progressively, people have become much better in how to use them, deploy them. So prefetching works well for regular memory access patterns, as we will see. But prefetching irregular access patterns turns out to be difficult. What's a regular memory access pattern? Well, let's say you're accessing memory in a streaming manner. Address A plus 1, A plus 2, A plus 3, A plus 4, A plus 5. You can easily predict, right? If you're accessing memory in a random manner, well, it may be difficult to predict what to prefetch next. Multi-threading, this is one of my favorite topics, as you know. It works well if there are multiple threads, right? If you can somehow generate. And GPUs heavily employ multi-threading, as we've seen. Right? A warp consists of multiple threads that do the same thing, operate on different portions of the data. And also, you have many, many warps that are basically many, many threads. Right? This is good for improving throughput, overall system throughput. But what if you have only a single thread? This just doesn't work, right? Fine-grained multi-threading, we've discussed this. If you have only a single thread, you lose throughput significantly with fine-grained multi-threading. Out-of-order execution, this actually, as we've discussed earlier, this is a limited form of data flow. And data flow is the best way that we know of in exploiting irregular parallelism today, right? If you want to figure out dependencies in an irregular program, data flow and out-of-order execution is the best techniques. And as a result, you can now tolerate these irregular cache misses that prefetching doesn't work well. And by definition, caching doesn't work well because they're cache misses. And that cannot be tolerated via multi-threading. Right? The problem with out-of-order execution is just what we've seen before. You have a limited size of the instruction window. And if you want to tolerate really long latency misses, you need to increase the size of your instruction window significantly. So in this lecture, we'll talk about one specialized prefetching method that alleviates this problem with out-of-order execution, which we call Runahead execution. And this will hopefully give you an idea of this field of dreams that I talked about earlier. So this was a dream. You actually do the design and simulate, and hopefully somebody else takes it and actually implements it. And others have done it. So I'll go through this really quickly. So you see that problem, right? Basically, this load, if we had one more entry in the instruction window, we could have parallelized these 2 really long latency misses. Right? The question is, how do you actually create that one more entry? Let me actually So simulation, again, field of dreams, right? You have this reality. You're stalling for most of the time. How would you actually get the potential benefit of increasing the size of the window? Well, in simulation, you increase the size of your window, right? It's actually easy if you write your simulator in a modular way. And if you increase the size of your window, it looks like this. Basically, this is the performance, average performance, of all of these applications on a machine that has a 2048 entry window. The reorder buffer size is 2048. And the other resources are sized, scaled, such that it corresponds to this 2048 entry window. And if you look at this, this buys you significant performance, right? The performance improvement is about maybe 33% over here, which is good. And you don't stall as much anymore. Does that make sense? So the question is, how do we actually get close to this without building this huge window? Well, let me restate the problem. Basically, you need these large instruction windows if you want to tolerate today's main memory latencies using out-of-order execution. As main memory latency increases, the instruction window size should also increase to fully tolerate that latency. The problem is building this large window is a challenging task, especially if you would like to achieve low power and energy consumption, because building a large window requires more buffers, more reservation stations, and tag matching logic becomes more complex, if you remember from what we've discussed. Load store queue becomes more complex. If you want short cycle time, again, building a large instruction window is not a good idea, right? Because now your wake up and select latencies, if you remember the out-of-order execution lecture, those increase because you're increasing the size of your window. And your design and verification complexity actually shoots up as you increase the size of these structures. So efficient scaling of this instruction window size, how to do this efficiently, is actually one of the major research issues in out-of-order execution and data flow today, actually. How do you achieve the benefits of a large window with a small one, or in a simpler way? In fact, if you look at the progression of Intel and AMD processors, they've already done this, a lot of it. They've already figured out a lot of ways of making the out-of-order structures a lot more efficient over time. They use a lot of different tricks such that they utilize, they make the best out of the small resources in the window. We're not going to go over those, but we'll talk about some other ideas. So yeah, how do you achieve the benefits of a large window with a small one, or in a simpler way? So one example that we've discussed was Bloom filters, right? If you actually use Bloom filters to eliminate some load store queue searches, that improves the efficiency. But that doesn't buy you more latency tolerance, that just improves the efficiency of the window. So this kind of tricks have been employed in modern designs a lot. Okay. How do you efficiently tolerate memory latency with the machinery of out-of-order execution and a small instruction window? If you remember, we talked about memory level parallelism. I'll go through this really quickly because that's what we're going to try to achieve, right? If I remember the picture I showed you, 8 under instruction window, the last load miss cannot get into the instruction window. As a result, it cannot be parallelized. Well, that may be the actually most important instruction, right? Because that will take 500 cycles. And you're keeping the window busy with some instructions that are just one cycle execution, right? The green instructions that I showed you earlier. It may make a lot more sense to actually somehow create space in the window such that you can fetch the next instruction, generate the cache miss associated with it, and service it in parallel with the original miss. So basically, a better thing for performance is to maximize this misses, or actually make all of the misses parallel as much as possible, right? Instead of having, assuming you keep the same number of misses in a program, instead of having them in an isolated manner, have them in parallel. Right? This enables latency tolerance because you overlap the latency of longest latency things in your execution stream. Then the key question is, how do you actually generate these multiple misses? Out-of-order execution has some ability to generate it, but it's limited by the instruction window size. So we'll talk about Runahead. So Runahead basically is built upon this observation. We want to enlarge the size of the window, but we don't want to pay the cost for it. So can we actually somehow obtain the memory level parallelism benefits of this large instruction window without actually increasing the size? And you can. That's the answer, basically. That's why we're talking about it. What you can do is, this is how it operates. When the oldest instruction is a long latency cache miss, in the window, you can checkpoint the architectural state and enter a special mode, speculative, purely speculative processing mode called the Runahead mode. In Runahead mode, you can speculatively pre-execute instructions just like normal execution, except you don't update this architectural state. And the purpose of this pre-execution is to generate the prefetches, generate those cache misses. Remember that instruction, that poor instruction that couldn't enter the instruction window? Well, if you checkpoint the architectural state at that point, you can start removing instructions out of the window, and you can create space in the window for the next instruction to come, and that will generate a cache miss, and you can start that cache miss early. Okay? And of course, some instructions you cannot execute, right? Because you entered this mode because the oldest instruction is a cache miss, and these cache miss instructions are marked invalid, and they're dropped because you don't have the data for them. So anything you don't have the data for, you can drop them, right? And when Runahead mode, when the original miss returns that caused entry into this mode, you stop the speculative execution mode called Runahead mode, and restore the checkpoint, and resume normal execution by going back to that instruction and executing it non-speculatively. Does that make sense? OK, let me give you a pictorial view of it. So ideally, what you want is perfect caches you never stall, right? Again, we're dreamers. We'll try to do as ideal as possible. But what you get today, with a small window, is you get a cache miss, and soon after, your window becomes full. As a result, you stall for a long time. And later, this cache miss is satisfied. You can start retiring instructions from your window. You can compute. But after some point, you get another cache miss. And soon after, your window becomes full, and you start stalling again. So what Runahead does is, when you get the long latency cache miss, instead of stalling, you basically soon after that, the cache miss becomes the oldest instruction in the window. When it becomes the oldest instruction in the window, you checkpoint the architectural state and enter a speculative mode, Runahead mode, where you remove the instructions from the window and keep processing new instructions into the window. And because you can do that, now you're not limited by your instruction window size. You can actually fetch this load 2, right? And now you can actually execute it, assuming load 2 is independent of load 1. You can actually execute this load 2, and it generates a cache miss. It can start servicing that cache miss in parallel with the cache miss that caused entry into the speculative execution mode. And once this miss is done, you can flush the pipeline, restore the checkpoint, and fetch load 1 again, and re-execute everything again. And hopefully this miss is being serviced while you're doing all of this. And once you re-execute load 2, now it hits in the cache because this miss was prefetched, if you will, because instead of stalling, you did the speculative execution that generated that miss and started servicing it. And now you save cycles because the processor doesn't stall for the second miss. Basically, what you've done is, instead of stalling for this first long latency miss, we basically checkpointed the architectural state and kept processing instructions. And that allowed us to get to an independent cache miss, or independent instruction that generated the cache miss, and service that cache miss, and overlap the latency of that cache miss with this other cache miss and some computation over here. And by the time you really executed that instruction, you get a cache hit. Does that make sense? Yes, questions now. Yeah, go ahead. Yeah.
If you get a third load miss,
Yeah.
somewhere in that second Runahead part, then do you just extend it and you just keep going until you don't find any more misses?
So these are all design choices. That's a great question, basically. Now you're dreaming. Like, what do you do, basically? Do you actually stop here, or do you keep going? Right. Well, because, I mean, what I've shown over here is Runahead mode ends when the miss that caused entry into that Runahead mode actually returns. That's one design decision. But you could make the design decision, oh, maybe if I go a little bit more, I'll find more misses, right? And those may be actually useful. Okay. Yes?
Are you actually executing the instructions in the Runahead block, or are you just looking for loads?
So that's another great question. The simplest way is to execute everything that comes your way, right? If you're just looking for loads, then how do you skip? How do you figure out which instructions to skip, right?
In that case, are you using the results of
Yes.
Okay.
That's
so
right.
How do you?
So think about it as when you enter this mode, you're really executing the program. You keep going as if nothing has happened, except some values, the value that was being loaded by load 1, you mark that as invalid. You don't know that value.
Okay.
It's not valid in the register file. So if I draw this, let's see. Well, I already have something here, but that's okay. No signal. I guess there's a reason for it. Okay. That's a stall. We could be doing Runahead now. And prefetching. I could have done it, for example. I could have actually kept drawing over here. Right. Okay, so you have this instruction window. You get a load. Let's say it's loading into R1. And then let's say this is a branch that's using the result of R1. And then you have add, multiply, ... Your window is full. This is the oldest instruction. This is the youngest. So normally you would stall here, right? But this load, you figure out it's a long latency cache miss. You say, oh, I'll enter Runahead mode. What I will do is I'll checkpoint the architectural state. Basically, make a copy of the register alias table, the retirement register alias table. That's the simplest way of doing it, right? Or you could copy all of the register file. That's another possibility. But you basically checkpoint the register file. So this is what you're going to return back to. You checkpoint the program counter of this load such that you're going to re-execute it again because you don't have the value. The goal is to remove this instruction from the window. Now all this becomes this. But what you do is you mark R1 that you're going to use later on in Runahead mode as invalid. So basically you have validity bits saying, do I really have the result of this R1? And invalid means no, I don't. So basically, to enter Runahead mode, you take the destination register over here and mark it invalid. Okay? Now this branch instruction, if it sources that value, well, it's invalid, right? If you predicted it correctly, that's great. But if you mispredicted it, you will never know whether you mispredicted it, right? So you get rid of the branch from the window also. Now you've created 2 entries in your window. Well, this poor load that couldn't have entered the window, now it could enter the window. Now you could execute it. Well, why? How can you execute it? You can execute it assuming it doesn't depend on R1, right? If it depends on all of these instructions that are independent of this R1, now you can actually compute its address. You can rely on that computation. And it generates an address that it would have generated anyway, right? Because it has nothing to do with R1. Make sense? Basically, we're just creating space for these loads, independent instructions. But in the meantime, we're analyzing all of the instructions in the program, just like out-of-order execution does, figuring out. So what if you have an instruction that's dependent on R1? Let's say you fetch an instruction over here at R1, maybe add doubles, R2 is 2 times R1, right? Well, what happens over here is you figure out that R1 is invalid when you execute this instruction. You mark R2 as invalid also, because you don't know the result for it, right? Basically, this bit specifies the fact that a register is dependent on some missed whose result you don't have yet. That's what invalid stands for. That way you can distinguish valid results and invalid results. And valid results are results you can trust. You can use them for prefetching, address computation, and you can use them for branch resolution also. Okay? Yes?
Can you also do stores?
So let's get to it. You can definitely do loads because they don't affect memory. You can prefetch the stores, but you don't want to update memory with this, right? It's the same thing again. This is a purely speculative execution mode. You don't update any architectural state. That's why we checkpointed the architectural state to begin with. So let's take a look at the how this actually works in a little bit more detail. But let me tell you about the benefits first. Basically, if you're pre-executing loads and stores in this mode, and again, it's purely speculative. You don't update the architectural state that's visible to software. As a result, these the ones that are independent of the L2MIS instructions generate very accurate data prefetches for both regular and irregular access patterns, right? Because you're really executing the program in the end. And instructions on the predicted program path are prefetched into the instruction or trace cache in L2. And actually, we'll talk about hardware prefetcher, but branch predictor you know already. You can actually train these tables using future access information, right? This could be a good or bad thing, actually. Let's take a look at these mechanisms. First of all, you need to somehow enter Runahead mode, and you need to somehow checkpoint the architectural register state. And I already told you how to do this, right? You actually need to checkpoint program counter also so that you can return to it. And remember, when we talked about branch prediction, you may actually want to checkpoint the global history register as well, because what you're really doing is you want to execute the program speculatively and then come back to the point where you were in the program. If you actually update the global history register and come back again and use the updated values, well, you actually messed up with your global history register, right? Because you updated with stuff that's in the future, in a sense. OK, let's take a look at instruction processing in Runahead mode. This will answer a lot of your questions. Basically, it's the same as normal instruction processing. Think about out-of-order execution. We're doing exactly the same thing. If it's in-order execution, we're doing exactly in-order execution, right? So for example, in-order execution, if a data value is not ready, you could do Runahead, right? You could actually keep going and invalidate all of those things. Except there are two differences. One is it's purely speculative. The software visible register or memory state is not updated. And these instructions that are dependent on L2 misses are identified and treated specially. What does this mean? They're quickly removed from the instruction window. If the result of an instruction is not ready, if it's an L2 miss, it shouldn't waste space in the instruction window, right? Because I could fetch something that's hopefully not dependent on this cache miss, and that will be useful. That's the first thing. The second thing is their results are not trusted, right? If you have register 1 over here, well, you actually don't have register 1 because the value is not available, so don't trust those results. Well, you could actually do something else. You could predict those results, right? If you have a good value predictor, you could say, oh, I'm going to predict the value and use that. And it's OK, because this is purely speculative, right? No harm will be done if you actually generate an exception, because you won't generate an exception in the end, because it's purely speculative. You never handle an exception that's purely speculative. An exception is handled only if it's really generated by an instruction that you're supposed to execute, really. Here, we're just doing this for prefetching. OK? So basically, two types of results are produced in this mode. Invalid means it's dependent on an L2 miss. And these invalid results are marked using invalid bits in the register file and the store buffer. Basically, your register file needs to be augmented with these invalid bits. Store buffer also needs to augment it, because you may actually store using you may actually store invalid data, right, to an address. And a dependent load should not trust the data if it's loading from a store that is storing invalid data. Okay? And invalid values are not used for prefetching and branch resolution. Again, this is a design choice also. Remember, this is a speculative processing mode. You can say, oh, I'm going to predict the value. I'm going to use these results. And if my prediction is reasonably accurate, maybe I'll get more cache misses that are correct. So how do you actually remove instructions from the window in Runahead mode? That's a little bit different also, because if you have an oldest instruction, you examine it for pseudo-retirement. And I call this pseudo-retirement because it's not really retirement. It's not really updating architectural state. It's really updating whatever is internal, microarchitectural. Architectural state is at this point is really the checkpointed state. And it's not really updating memory also. If it's an invalid instruction, it's removed from the window immediately. If it's a valid instruction, not dependent on a cache miss, it's removed when it completes execution. And a valid instruction, after executing, may become invalid because it may get a cache miss, right, if it's a load. Okay? And if it's once an instruction is pseudo-retired, it frees its allocated resources. This allows the processing of later instructions. That's how you remove this instruction from the window. And if you actually have pseudo-retired stores, you don't want to update memory, because updating memory changes the architectural state. Some other processor can take that value, right? Bad idea. But you may want to communicate their data to the dependent loads in the same thread. That way, you can hopefully get better execution in Runahead mode. And if you basically, you could do this in many ways. But one way of doing this is to have an auxiliary structure that enables this data communication through memory in Runahead mode. You don't want to update memory, but you have this store that's executing in this Runahead mode. let's assume that you have the store over here that's storing some data to address A, and later you have a load that's loading from address A. Well, how do you communicate between these? You can do it through the store buffer. But again, what if the store goes out of the store buffer, right? Because you're executing farther, because your store buffer is limited also. That's part of your instruction window. Well, if the store goes out of the store buffer, maybe you put the data in a little cache-like structure at address A. And later, when a load comes in, it checks not only the store buffer, but also this. If it misses in the store buffer, it gets the data from this cache-like structure called Runahead cache. And whose purpose is solely communication of data between stores and loads that are happening in Runahead mode. Okay? That's the idea, basically. And again, because everything is purely speculative, you don't need to be always correct. The size of this can be small. It doesn't need to be as complex as a load store queue, because you don't need to be correct. Yes?
So there are some independent instructions that you execute in Runahead mode. So when you restore your checkpoint, you don't want to execute them again. Right?
That's right, ideally. But then the question is, how do you actually figure out not to execute them? You have a good idea.
If they're not marked as invalid, I mean, those registers would have valid values, right?
Mm-hmm. Hopefully. But maybe you don't have anything because you run ahead so much. Remember, your register file is limited resource also. Whenever you pseudo-retire or remove an instruction, you're deallocating the registers. And somebody else is using those registers. Okay? So you may not actually have all of the values in the register file. But you have a very good point. Basically, you're actually doing all of this work, executing independent instructions. When you're coming back, we're re-executing everything. If we had saved the result somewhere, maybe we could avoid re-executing things. But that complicates the engine a little bit. Okay?
And is it just like specific to an L2 miss or?
No, actually, that's a great question also. You could potentially do it with any long latency instruction, right? If something takes, again, it depends. You could potentially do it in in-order machines. If you have an in-order machine where L1 cache miss takes a long time, you could do it, right? It's not specific. Okay, so let's take a look at branch handling. Basically, branch handling is exactly the same as a normal mode, except you have some unavailable data, right? You have some invalid branches that cannot be resolved. And this is not a problem if you predicted it correctly. You'll stay on the correct path. Right? The downside is if it's a mispredicted invalid branch, it causes the processor to stay on the wrong program path until the end of Runahead execution. Right? And you will not even know it during Runahead execution because you don't have the result available. But valid branches are resolved and initiate recovery if mispredicted. So it's like the same as normal execution, except invalid branches cannot be resolved. And this could actually cause problems, right? You're on the wrong path, and you may be prefetching wrong stuff. But you may actually be prefetching correct stuff on the wrong path also. Why? Because the wrong path may actually reference stuff that's going to be needed on the correct path. And more often than not, this is actually true in many programs. A lot of the analysis of programs have shown that it's better to go on the wrong path and execute than not go on the wrong path and execute. If you have to go on the wrong path, of course. Does that make sense? And you could determine this in simulation again, right? That's another beauty of simulation. You could say, oh, do I get benefit from executing on the wrong path or not? If you have to go on the wrong path, it's better to go and execute such that you actually generate some cache misses that could later be used for the correct path, as opposed to not doing it. And how could you model it? Well, again, you're the architect. You design a simulator where you know exactly whether or not you're on the wrong path while you're simulating. And one version of the simulator, or one run of the simulator, you enable a knob that says, while I'm on the wrong path, I'm going to service all of those cache misses that happen. And another version of the simulator, while I'm on the wrong path, I'm not going to service any of the cache misses. Right? Does that make sense? Yeah.
How do they know if it's on the wrong path?
Well, that's the beauty of simulation.
How do it knows which is the right path?
Yeah, how do you know that? Now you're going into the guts of simulator design. Well, as an architect, okay, let's think. In earlier versions of your labs, Lab 1, you designed a functional simulator. Can you actually combine it with a timing simulator? Functional simulator, very quickly, it tells you whether you're on the wrong path or correct path, right? Because you're really feeding this program. This functional simulator. Basically, you can decouple functional simulation and timing simulation. This functional simulator can run actually, you can figure out all of what happens for all of the instructions and store it, and then derive the timing simulation that way. Because timing simulation basically tells you how long an instruction will take. Right? With functional simulator, you can easily figure out, oh, I'm executing this branch. Its correct path should be taken. And then you can actually consult the branch predictor that you're trying to implement. But the branch predictor actually tells me I should predict it not taken. Right? Now you know that the branch predictor that you implement over here is actually wrong. And this is software. So you can actually make a note of that saying, oh, I'm actually on the wrong path in the timing simulation. Right? You can model everything over there, and you have a knob that says, oh, while I'm on the wrong path, I'm not going to generate the cache misses. Right? That's actually how many architectural simulators are designed today. You do the functional first simulation, such that you have a lot of information about what the program does, and then you can actually change the timing. So how do you simulate perfect branch prediction, for example? Exactly the same way. Right? You do functional simulation, and you don't have a branch predictor. You always predict correctly, and you look at the timing of what happens. Right? Okay? So that's how you can analyze a lot of the design decisions you make. But that's a great question. OK. We still have some time. So this is one design of the Runahead process. Now, I'm not going to go through this. You've seen this picture before. But what do you need for this? Basically, you need to have the ability to checkpoint. This is basically a copy of the retirement thread at the time, retirement register alias table, at the time the load is at the head of the reorder buffer. And you need invalid bits in the register file. And you need also some other things like program counter over here, global history register, return address stack also, because these things, you really want the context at the time you actually finish this load. And this is the Runahead cache that we talked about. The purpose is just memory communication during Runahead mode. It's not an architectural structure. Let's take a look at the advantages and disadvantages of this. So advantages, it turns out this is actually very accurate for prefetching, because you're really following the program path, right? Instead of stalling, you just keep going, right? Except doing it speculatively. So as a result, you get very accurate prefetches. I call them prefetches because later you're going to re-execute the instructions. And the first pre-processing, if you will, is a prefetch. The first time you execute that instruction, you're pre-executing it. Right? Okay. It's simple to implement because most of the hardware is already built in. Right? You're really reusing this out-of-order execution machinery to do this prefetching, if you will. And we'll see in the next lecture or two other pre-execution-based prefetching mechanisms. You don't need to understand all of this now. But what we're really doing is you're using this thread context. So other pre-execution-based prefetching mechanisms, which you can use in existing processors actually, you can launch a thread on some other core that does prefetching for you. Right? You can launch a thread on some other thread context if you have a multi-thread processor that does prefetching for this main thread. Okay? Well, in this case, you don't need to construct that kind of thread, right? In a sense, when you get a cache miss, you're automatically using the main program thread to do prefetching. OK, there are a bunch of disadvantages and limitations. If we had time, I would ask you all of these one by one. But now I'll go through this quickly. Yes?
If you're doing checkpointing,
Mm-hmm.
then why are you waiting for the load to become the oldest instruction?
That's a good question. That's because you need to do the checkpointing nicely, right? If the load is the oldest instruction, your retirement register alias table already constitutes a good checkpoint. Otherwise, how would you construct that checkpoint? I'll let you think about that. It's not that easy. Because you don't have a checkpoint associated with a load normally. Right? Normally, you can associate a checkpoint with branches, assuming you do employ checkpointing, as we've discussed. But when you fetch the load, you don't have a checkpoint associated with it. Right? And if you wait until the load becomes the oldest, the architectural state at that point is really your checkpoint. That's true for any instruction, by the way. If you want to checkpoint the state of a processor at any point, you wait until that instruction becomes the oldest. OK, the disadvantage, clearly this executes more instructions, right? If you get cache misses, you're executing the instruction stream once, and then you're going back and re-executing it again. And you could do it many, many times, actually, if you keep getting lots of cache misses. You're limited by branch prediction accuracy, right? If your branch predictor is not correct, then you're not resolving the branches that are dependent on cache misses. But this is actually true for any large instruction window. If you are building a large instruction window, you'd better back it up with a good branch predictor, right? Because in the end, you're really fetching lots of instructions. And if your branches are not predicted correctly, you won't get a lot of benefit. That's another downside, right? You cannot prefetch dependent cache misses. If the next cache miss is dependent on the previous one, well, you're out of luck, right? Because you cannot even execute it in Runahead. Well, you can think about how to fix this problem potentially, right? Maybe you can predict the values or addresses. And as long as you're approximate such that you get some useful cache line, well, maybe it's OK. Right? OK, so effectiveness is limited by available memory level parallelism, actually, in the end. Because you may actually enter Runahead mode, keep processing, and find nothing. Right? There may be no cache misses. And this is if the program doesn't have misses separated, independent misses separated from each other in close proximity, this doesn't work again, right? It turns out, actually, a lot of programs, when you get a cache miss, it's likely that you're going to get other cache misses. This is called the people have analyzed programs a lot, and they figured out that misses are kind of clustered together. You get a lot of cache misses, and then you compute, and then you get more cache misses. It kind of makes sense, right? You're bringing in a lot of data, operating on it, and then bringing in some more data. Especially if you do good blocking, for example. Let's think about some regular programs. If you do good blocking, that's how it works. OK. And prefetch distance is limited by the memory latency. Prefetch distance, in this case, how far you can go ahead, right, in Runahead mode. It's really limited by how long your memory latency is, right? So it's actually, there are some really good papers that describe how this is done in Sunrock. And IBM Power 6 says it also. There are several papers on that. But let's take a look at the performance of something like this. Again, we've started out with simulation, so I would like to talk about some simulation over here. These are all simulation results on the same process that I showed you earlier. And these are, again, workload suites that Intel used to build processors at the time. These are spec benchmarks, some web workloads, multimedia workloads, some productivity, server, workstation workloads. I believe Verilog is one of them. Verilog simulation, for example. You can actually speed up Verilog simulation. It turns out it's very, very memory intensive. So basically, you can simulate multiple processors to see multiple different configurations to see the benefit of this. Basically, this is a processor that's really a terrible baseline. No prefetcher, no Runahead. This is a processor that has some prefetcher, which we will talk about in the next lecture. It's a streaming prefetcher, basically A plus 1, A plus 2, A plus 3, A plus 4. If you're doing this, it's great. You can actually prefetch well. It's actually more intelligent than that. It can capture a lot of streaming patterns. So this shows you that actually adding a prefetcher buys you a lot of performance. This is average across all workloads. And this is in terms of micro instructions per cycle. And this is what the performance you get if you do only Runahead execution. So it's better than the prefetcher. But the best benefit you get is when you combine the prefetcher and the Runahead. And this 22% is on top of the baseline with the prefetcher. Anyway, you can take a look at the paper. So how does this fare compared to the large windows? It turns out it gets, basically, this is the baseline with prefetcher, 128 entry window. This is if you increase the window size, if you triple the window size, 384 entry window out of order processor. So Runahead gets very close to that. So it kind of gets most of the benefit, right, of a triple size window. But if you analyze the results, actually, sometimes a large window is better, sometimes Runahead is better. And hopefully you can imagine why that's the case, right? What do you guys think? I'll ask you some questions. Which can tolerate the FP operation latencies better? Right? So Runahead cannot do much about short latencies, at least the way I described it. Right? If you have a 20-cycle latency floating point instruction, well, out-of-order execution actually can tolerate that nicely because its window size is good enough for that because I showed you 128 entry window in this case, right? It's all a matter of how large your window is, how much latency you can tolerate. Whereas Runahead, well, it doesn't help. So if your FP operation latencies, let's say you have a dependency chain through your floating point operations, you never enter Runahead mode, but a large instruction window can tolerate those latencies much better. So in this case, a large instruction window is a better idea than Runahead, right? Which leads to less wasted execution. So hopefully this is clear, right? A large window doesn't lead to as much wasted execution as Runahead. Why? Because you're not really going back and re-executing. A large window does lead to wasted execution still. Why? Because your branch prediction accuracy is not good enough, right? Because if you have a large window, actually a small window is more efficient because you're not as dependent on your branch prediction accuracy because you're not fetching this branch that's mispredicted, hopefully. Because you have limited window, you wait until you fetch a mispredicted branch. Whereas with a large window, you'll fetch everything you can see, well, everything you can. If there's a mispredicted branch that you cannot recover from, you'll execute some instructions until you recover from that branch. So you waste a lot more execution than a small window. But Runahead wastes still more. OK. We can actually imagine other questions over here. So it's a pro and con analysis again. Okay, let's take a look at a couple more things before we finish today. So this idea itself, again, we're dreaming, right? Again, we can simulate in order versus out of order. You have a simulator that you can configure to execute as in order, and then add Runahead on top of this. It buys you some performance. It turns out it's pretty significant, about 40%. And you can simulate it as out of order to model the execution of out of order. It actually buys you a lot compared to in order. In this case, it's a huge, I haven't calculated it, but it looks pretty large, right? So an out of order execution is much higher performance than in order execution here. But on top of that, if you add Runahead, you still get some. So if you look at the relative benefits of Runahead over in order and out of order processors, it's much more beneficial on in order processors, right? Why is that? Because in order processor cannot tolerate any latency, right? That's not exactly true. You can actually tweak it. It's actually a tweaked in order such that you don't stall on every. You don't stall on a lot of things over here, but still, you need to stall on real dependencies, right? So because you cannot tolerate any latency, adding another latency tolerance mechanism buys you a lot more performance over here. Whereas out-of-order execution can tolerate some latency. As a result, adding Runahead doesn't buy you as much performance as it would if you added it on top of in-order execution. So this is all good and well, but it's all in simulation still, right? And actually, this was a slide. The designers at Sun, which unfortunately doesn't exist, it's Oracle now. Oracle bought Sun. Took this idea and they actually implemented it eventually. And this is one of the slides they had. They called it Scout threading at the time. This is one of the slides they had, which I really like because it shows different trade-offs in design. And you cannot get the slide if you actually do RTL simulation. This is actually across on commercial workloads on their processor design. This L2 cache size on the x-axis, normalized IPC on the y-axis. This is if you do in-order execution without Runahead, no Scout. And this is if you add Runahead on top of this. That's the performance benefit. So with a 512 kilobyte L2 cache, you get 40% performance improvement if you add Runahead execution on top of that. It's actually, interestingly, very similar to the result that we got. I was pretty happy when I saw it. Somebody else validated our simulator with totally different ISA and totally different model. And you can actually trade off things. So if you have this kind of latency tolerance mechanism, you can design a 1 megabyte cache with Runahead, and that gives you, for this workload, for these workloads that they evaluated, the same performance as an 8 megabyte cache with no Runahead. You can actually save a lot of space. And you can actually, at different points, you can actually save different amounts of space, right? It's really interesting. So this is the kind of trade-offs that you can do if you have a high-level simulator that you really cannot do at low-level simulation, right? Does that make sense? OK. I think this is a really good place to stop. Any questions? All right, I'll see you. When is that? Wednesday. Yes.